My name is John Gilbertson, and I'm an associate professor at Western Washington University, and I'm using the Henry Dreyfus Teacher-Scholar Award to do research on moving protons and electrons in a bio-inspired fashion, which is just a fancy way of saying that we are borrowing nature's ideas to do useful chemistry.
Hi, my name is Christopher Aguayo. I am an incoming senior and a fourth-year chemistry student.
I'm Wyatt Parks. I'm an incoming junior and I'm studying biochemistry. We're working on taking pollutants from fertilizers and converting them to less harmful or potentially useful compounds.
So there are several ways that somebody would tackle an issue like this. A biologist would maybe want to study the enzyme that does this, but because this is a bioinorganic chemistry lab, we focus on the active site of the enzyme and mimic by creating a compound that can do the same chemistry, but is significantly much smaller and easier to reproduce than the enzyme.
So in the nitrogen cycle, nitrates or nitrites are reduced to other compounds, and one of those intermediates is NO, nitric oxide, which from there can go to other compounds.
So the reason why we'd want to go to NO is because if we can add a proton to the nitrogen, then we're just one step closer to creating ammonia. And ammonia can be used as a fertilizer. If we were able to do that, we'd accomplish our goal of turning pollutants into something that's useful again. So we know of a compound, we call it PDI. It's redox active, so it means it can store electrons. And the importance of that is that the transfer and storage of electrons is how chemical reactions take place. So in the situation where we're trying to break down these pollutants, we need to take away or give electrons, and the PDI can actually do that.
So we take our PDI ligand and we bind it with iron or some other cheap, abundant transition metal, which then can go on to reduce nitrite to NO, or nitric oxide. So transition metals are things like iron, copper, cobalt, and they're relatively abundant and cheap. So if this method successfully can catalyze nitrite into more useful things, then these compounds will be relatively cost-effective. This is foundational research that will hopefully help future researchers come up with a solution to pollutants from fertilizers.
We'd like to thank the Dreyfus Foundation for giving us the funding to have these kinds of experiences as undergraduates. It's very useful on our career path and what we decide to do with our undergraduate chemistry degree.
Because of this, we actually do real chemistry, so it's a great opportunity for us.